Okay, so we're just going to go through some working for exercise 10E of the Pearson Applied 1 textbook on connected particles. Now this is a topic that people typically find quite challenging. Basically, if the particles are connected, we're looking at a system of particles which are connected by either a contact force, a string, or a rod usually. And the important thing to consider is that sometimes we want to look at the whole system as one particle and treat it as one particle. At other times, you'll want to consider the particles individually, in which case we just need to look at the forces that are directly acting on those. So we'll go through some examples to start off with. So two particles P and Q of masses 5 kilograms and 3 kilograms respectively. So P is 5 and Q is 3, are connected by a light inextensible string. You need to be careful about those wording and make sure you understand what they mean and how they affect our calculations, because they come up every year in exams. Particle P is pulled by a horizontal force of 40 newtons along a rough horizontal plane. So think about what rough means. It means we're going to have to consider friction. Particle P experiences a frictional force of 10 newtons and Q experiences a frictional force of 6 newtons. So obviously there's a lot of information there. So we're going to start off by, we're going to put that in a diagram. So the things we're trying to calculate, first of all, we're going to find the acceleration, we're going to find the tension in the string, and we're going to explain what those words mean, light and extensible. So first of all, we draw a diagram. So we've got two particles connected by a string. We want to label all the forces on there. So there's a 40 Newton driving force, 10 Newton frictional force on P. There's the weight of P, which is 5 G. And then we've got a reaction force on P, a normal reaction force. And then tension with the string pulling P. And then obviously on Q as well, we also have a frictional force. We have a weight force of 3G newtons. And a normal reaction force on Q of R, and obviously the tension is also acting on Q. Now, for part A, we want to find the acceleration of the particles, so mark on the acceleration as well, which is going to the right. So for part A of this question, we want to find the acceleration of the particles, and because the acceleration is the same, we can take the whole system as one thing, and that means that the tensions will cancel out, so we don't need to consider the tensions. So if we resolve horizontally, we're going to use F equals ma. Obviously, as we know, we need to use the resultant force for F. So it's going to be 40 minus 10 minus 6 equals mass times acceleration. And we know that the mass altogether is 8 kilograms. So then we can solve that quite simply to get A equals 3. So we know the acceleration is 3 meters per second squared. And it's always a good idea to then mark that down on your diagram so you've got it there visually. Next, we want to find the tension in the string. To do that, we'll consider the particles individually. Now, you could do this with Q or you could do it with P. Both of them would work. Personally, I'd go for Q in this case because there are fewer forces acting on it and it'll make it a bit easier. So if we resolve horizontally, taking the right direction as positive, that makes sense because we've got the acceleration going that way and also the unknown is going that way. So we do F equals ma again. So the forces acting on Q, we've got tension going to the right and 6 newtons going to the left, and then the mass is 3, so we get T minus 6 equals 3 lots of 3. So if we solve that, which is reasonably straightforward, we should get T equals 15 newtons, and that would be the same for both values of T. It will always be the same. Okay, then explain how the modelling assumption the string is light and inextensible have been used. This comes up every year, make sure you understand this. So the fact it's light means that the tension is constant across the whole string, and the inextensible bit means that both particles will have the same acceleration. Okay, very important. Okay, now we're going to look at an example of a scale pan. These are probably the connected particles questions that people find most tricky. Okay, so a scale pan is attached, sorry, a light scale pan, very important. The fact that it's light means it has no mass, we assume it has no mass, is attached to a vertical light inextensible string. The scale pan carries two masses, A and B. The mass of A is 400 grams and the mass of B is 600 grams, and A rests on top of B. The scale pan is raised vertically and is accelerating at 0.5 meters per second squared. So we need to find the tension in the string, the force exerted on B by A, and the force exerted on B by the scale pan. Okay, so obviously we're going to begin by drawing a diagram. So a scale pan just looks like this. It's basically just the pan that would be on a set of scales. And we've got these two particles on there. So we've got the tension already going upwards. There's no weight for the pan because it's light, so we're assuming it has no mass. So then we have the weight for particle A, which is 0.4 g. Remember, we work in kilograms. And for the mass, it's 0.6 g. Okay, and we know it's accelerating upwards with an acceleration of 0.5 meters per second squared. Right, so if we want to find the tension in the string, we want to consider the whole system as one particle. Okay, so we're going to do F equals ma, resolving vertically, so we get F is of course the resultant force, so we need to consider all the forces going vertically. So T is positive, and then we've got 0.4 g and 0.6 g going downwards, and the mass of the whole system together is 1 kilogram, and the acceleration is 0.5. So now if we solve that, so simplify it first of all and then solve, we get T to be 10.3 newtons. Okay, so we now know what tension is, so we'll mark that on a diagram. Now we need to find the force exerted on mass B by mass A. Now, the interesting thing here, instead of looking at particle B and working out what force is being exerted on it by A, that would be trickier because we've also got a reaction force on B from the scale pan. So instead, we just look at the reaction force between A and B, and it'll be the same going in both directions. So because particle A only has B acting on it and its own weight, that would be a simpler one to use. So we'll work with particle A and resolve vertically. So we know we've got the weight of A and we've got the reaction force from B. And we know the acceleration, because it's the same as the scale pan, is 0.5 meters per second squared. So now we can use F equals ma. So we have r minus 0.4 g. The mass is 0.4 and the acceleration is 0.5. So we can solve to get r as being 4.1 newtons. Okay, so we know that the force acting on B from A and on A from B have to be equal. Okay. Now we want to find the force exerted on mass B by the scale pan, so this is where we'll now consider mass B, because we know the reaction from A, so we can work out the reaction from the scale pan. So just draw particle B, so it's got its weight, it's got a reaction from A, and it's got a reaction from the scale pan. So we have weight going downwards, reaction from A going downwards, and obviously the reaction from the scale pan is going upwards. And again, the acceleration is still 0.5 meters per second squared. So now if we use F equals ma, using our resultant force as always, resolving vertically, so we have S minus 4.1 minus 0.6 g equals 0.6 times 0.5, that's mass times acceleration, and you get S is 10.3 newtons. And so these sorts of questions are the ones that students find most tricky, so make sure you go through plenty of questions of this type, ask for help if you need it.